Hi, and hello everyone that is joining us today, and thank you very much for joining us. So today we have a very good set of presentation and talk. So you can see on the screen there the presentation we will get. So I will be the moderator of today. So this is our ninth student webinar. And today we will be discussing the volcanic contributions to the stratigraphic record. But before starting properly on the talk, we would like to thank the sponsor, the IIS, who makes everything that we can see today possible, like the webinars, and providing them for free to everyone, and also accessible to be watched or rewatched weeks later online on the sedsonline.com website. So if you haven't checked yet, please go check. Not only the student webinar, but there is a series of other webinars that we have, the monthly webinar, so you can access all for free on the website. So today we will have 3 talks. That each talk will be 10 minutes long, and there will be 5 minutes for questions after. So if you have questions for any given talk, you will see that towards the end of the presentation, the chat will open. So we will ask you to please write down your question in the chat with your name and your affiliation and where you're from. And then I will read them to the speakers after, and they will be able to provide an answer directly to you. So also, if you don't have time to write the question before the end of the question session, please keep writing them and letting us know who they are for, and we can stay at the end and organize a panel discussions afterwards if there is any further questions that we can see. So if we can. I would say that we can now start, and our first presenter of the day will be Nils Baumann. So I will stop sharing my screen, and Nils, you can start to share yours if it's okay with you. Alors, stop sharing. Up.
So give me a second.
Yes. Yeah, all good.
Does that work for everybody?
Yeah.
Okay, great. Then let me just get my laser pointer here. Okay, so thanks a lot for inviting me, and also thanks to all of you attending today. So in the next 10-ish minutes or so, I'm going to present to you the research we've been doing for the last 2 years or so, and it's on Tellurium as a novel proxy to unravel the intricate history or link between LIPs and mass extinctions. So just as a refresher, when we talk large igneous provinces, what we basically mean is the largest volcanic features on Earth. And apart from their sheer volumina they're erupting, what makes them interesting is actually that they're placed over relatively short time spans. So usually we talk less than 1 million of years. Also, as you can see on this map here, we usually divide them into continental flat basalts and oceanic plateaus. Now, the interesting thing is when we look at their evolution through time, they happen to coincide with also the biggest mass extinction events in history, in Earth's history, so to say. And so we're not just looking at these large magmatic futures, but also at these mass extinction turnovers like happening during the end Permian, end Triassic, but also end Cretaceous, one of the most famous ones probably. What is kind of a problematic thing here is that we have 2 different rock records, right? So we have sediments recording environmental perturbations, including mass extinctions. But then the whole magmatic history of LIPs is, of course, recorded in their magmatic rocks from the source volcanics. Also, just a small little thing, sometimes we get kind of superimposing effects where the debate starts to whether which one is more important. As for late Cretaceous, as you might all know, we also, for example, have bolide impact. Now, what we do to unravel this link is we look at geochemical proxies. And so for the past few decades, mercury, sedimentary mercury, has come up as kind of the standard. Now, while that sure has shown to be, or has shown to work, there's some complications linked to it. So first of all, as you can see, just on this nice little figure by Graspy, is that mercury is highly mobile. So there's a lot of source to sink processes going on. And then also one of the major problems we're facing is that kind of the main phase mercury comes with is organic matter. And so usually you normalize it to total organic carbon, but that comes with its own set of problems, because the thing is that measuring TOC or let's say below a certain threshold introduces a whole lot of problems, and then you get false negatives and false positives and so on. So what we've come up with is an alternative being in Tellurium. And as you can see on this nice histogram by Zelensky et al. From 2013, they measured volcanic gases at Erta volcano in Ethiopia. And they actually found that Tellurium is the most enriched trace element in these volcanic gases, even above sulfur, actually. And that's not the only advantage that comes with it. Moreover, what we find is that there's a very limited set of natural resource or sources for Tellurium. And so that makes it interesting as well. Last but not least, when we measure Tellurium, we usually measure thorium with it. And it so happens that thorium acts as a nice normalizing agent for us, because as it is mostly reflecting the detrital fraction coming in, and is not comprised in carbonates or volcanic gases, we can normalize by it and kind of counter the effect of changes in sediment lithology. So when we go into some first results that I want to show you, we are looking at the Wadi Nukul section on the Sinai Peninsula, Egypt. And the really neat thing about this section is when you look at the lithologue, it actually spans all the way from the late Maastrichtian up to the Eocene. What that means for us is it encompasses actually two LIP events. So once the Deccan traps here around the Cretaceous-Paleogene boundary, but then also the North Atlantic Igneous Province up here at the Paleocene-Eocene boundary. And just from a first glance at the tellurium chemostratigraphy, you see when you look at the circles that are just the tellurium concentrations, there's clearly something happening here. So first around the KPG here, we got two distinct spikes, and then also another very prominent one up here at the Paleocene-Eocene thermal maximum that marks the Paleocene-Eocene boundary. And so the same goes if we look at the normalized values, it's all the same. And while mercury does reflect some of these spikes, especially up here at the PETM as well, it's also clear that there's stuff happening in between and that it's not working to the same systematics. And so we think, or what that tells us, is that there are either non-volcanic effects at play for mercury, or it's recording non-LIP volcanism. And so that's not what we want. Now, just as a last thing here to show is when you look at the panel C here, it's also very interesting that when we look at tellurium-thorium ratios against mercury TOC ratios, in this blue phase, which marks the KPG interval, and also in the black phase that kind of marks the first spike, and the yellow, which is the PETM, we always get a relative increase of tellurium-thorium over mercury TOC. And so there's another thing we need to do here, because with the normalization, we take into account changes in sediment lithology, but especially when we look at such a large, wide-span or long-spanning lithologue or section, we get the problem of changes in sedimentation rate probably. So what we want to do to counter that is we implement age models. That's also where we get onto, let's say, treacherous ground to some extent, because we rely on nanofossil zone ages, or in the best case, uranium-lead dating for ashes in between sediments. So, of course, these age models always come with their set of complications, so to say. But it doesn't matter too much to us, because what we want from them is we want to calculate sedimentation rates to then convert tellurium concentrations first into detrital tellurium fluxes that we do with assuming a background tellurium-thorium ratio out of the lowest values. And when we subtract that from our total fluxes, we are left with what we suggest is just the volcanic flux of tellurium. And so that's what we see here. Again, a nice evolution in black over the Deccan main basalt eruptions. And then again, a really high spike when we get to the main breakup phase of North Atlantic igneous province volcanism. And the thing again here is we see that tellurium fluxes are kind of muted in periods of no LIP volcanism, while again, mercury fluxes do show spikes that we actually do not want to see in a proxy. And so that gives us the idea that for at least this section and this time frame for now, it seems to work really fine. And so what we can do with this, and what we try to do is, of course, we try to get into some implications for environmental change or mass extinctions. And so that's kind of the same graphic as before, the same plot as before, just here in the yellow panel, you see a blow up of the kind of Deccan traps and placement time frame, and in blue for the North Atlantic igneous province time frame. And so what we see here when we combine fluxes and changes in temperature and the carbon isotope excursion is that, first of all, this late Maastrichtian warming, which is a very prominent warming period here, it coincides with the less voluminous, or at least less degassing related eruptions, which tells us that while volcanism must have contributed to this warming event, it could also very be that a large part of it was thermogenic degassing. Moreover, and more interesting is that the main degassing event, of course, spans also the extinction horizon, which you could interpret from that volcanism had at least a contributing effect to the maybe main kill mechanism that was bolide impact. And then last but not least, also these main fluxes coincide with the rather cooling side of it after impact, which could mean that we attenuated this cooling period. For the North Atlantic igneous province, as I said, we see main fluxes during breakup phase, which is really interesting, but also this coincides with the carbon isotope excursion, like the main negative part of it, which tells us that volcanic degassing should have played a major contribution to this negative, or to this disturbing of the global carbon cycle. So I'm running out of time. So just to make it quick, what our outlook is here, we want to publish about the methods soon to make this proxy available to the whole community, because we think it works really well. We, of course, have already expanded in space and time, looking at other LIPs and mass extinction events. And we're also working on source processes, especially because tellurium is very underexplored, and we want to see how it behaves in the magmatic system. Okay, with that, I'm already at the end. Again, thanks for joining here. If you have any questions, do ask them now, or also don't hesitate to reach me on these channels. Thank you.
Yeah, thanks a lot, Nils. So please, the chat is open. So if you want to ask any questions, write them down, and I will read them to Nils. So while we wait for some questions to come, I have a few ones. Sure. What type, is there any particular type of sedimentary rocks that you find more tellurium than others? And how different they can be in the terms of the quantity of tellurium you can have inside, you can sediment deposit inside.
So the thing is that we're what we found out so far is that, for example, carbonates work really good for what we're doing, because most of the times they have like steady, slow sedimentation rates, which is what we want to see, right? But then again, if we have a lot of detrital input, that can mean that we get also a bit of an increased tellurium signal, because while it's in very low abundance in crustal rocks, of course, that's where it comes from if it's not volcanism. But then again, that's why we always that's why we always presented normalized to thorium, because we can kind of counter these two effects. So yeah, when you, for example, when we can, we try to incorporate major elements as well. So we see that, for example, when we define it myself, when we look at thorium and carbonate, we see a very nice negative correlation. and the very nice one when we look at thorium and alumina. So that's why we always normalize it, because it counters these effects.
Okay. I have more questions. Then to carry on with a similar question, is there any biogenic effect? Because we know carbonates are not deposited rock, they are made. So is there any effect on the quantity of tellurium that the organism can catch while they grow, for example?
So we wouldn't have found it by now. But to be honest, one of the main issues we have here is that it remains really like unwell in its exploration. It's like tellurium. People who are using it are mostly coming from more of the ore deposit side. And so yeah, for now we didn't really find any effect of kind of the biological influence of it, but I don't want to put myself into a position now where I say no, definitely not, or yes. So
So yeah, so some questions that are popping. So Sarah from Houston, that is asking, okay, is telling excellent presentation, Nils. Are there additional analysis you'd like to complete to evaluate your question further?
so basically what we're already doing is we have if I understand the question right. So what we're doing is we're working on a few things now. The KPG section I showed here is just a very nice one. We hopefully have in the next month North Atlantic province paper coming out, which is consisting of 3 other sections, which are 4 in Denmark. It's a really famous one for PETM studies. Then Gubbio, which is actually mostly known for its iridium anomalies. And then also the SDP 550. So that's what we have. We're working on terrestrial samples now, which is also really interesting. So especially intratrapean sediments in the Deccan domain, because we want to see what the proximity to the eruptions actually does to the tellurium concentrations. We're also working on samples from the time frame of the Carnian pluvial event and see what Rangelia has to do with all of that and how that comes into play. So yeah, we're actually working on a huge load of samples right now that we all have to explore. But so far, what we've seen from the data, it looks really promising.
Cool. Then next question is from Stephen Lokier from Derby. Thanks for a great presentation. Very interesting. Excuse my ignorance on this. Are there any potential contaminants in terms of country rocks that may mess up this proxy?
Yeah, so when we look at contaminants here, of course, the obvious one would be if we're in some kind of tellurites setting, deposit setting. But that's an easy one to see in the field or from the samples, right? Then the next one, which is really important, is ferromanganese crusts. That's something we always have to look out for. And that's why we like to also cross-plot our samples where we might find these crusts against cobalt, for example, to see if we have any linear relationships going on. Then last but not least, or just what comes to my mind for now, is when you're in like abyssal deposition regimes that have really low sedimentation rates, you might encounter interplanetary dust particles, which can be enriched in tellurium. So these are like the few that come into my mind.
Yeah, Stephen said, thanks, that makes sense. Okay, I will take a last question then from Mubashir from Milan. That says that he's working on similar things with Thierry Adate. Can you please explain me if the PETM sections is far away from the LIP, like Himalayan settings? Then how can we interpret the thorium and the mercury signal in terms of their provenance?
Yeah, so I guess that's an interesting one. So yeah, we were mainly looking at rather close samples now when we talk about the North Atlantic East province. I know about the work on the Himalayas. I haven't seen the data myself. So that's why I don't really want to comment too much on it, because I don't know the setting and I haven't seen the data myself. Yeah, it's definitely a difficult question, because when you talk provenance, you of course need to know the setting, right? So yeah, maybe we can discuss that later, because I don't really I can't give you a good answer or a nice complete answer now.
Okay. Yeah. Okay, so I think we can maybe move on to the next presentation. So if you have any further questions on that presentation, please put them on the chat, and we can see to answer that later. Now, Nahuel, you're here. So if you can please share your screen, and we will see a second presentation by Nahuel Losano. And yeah, so if you can put the full screen, and I will mute.
Little spoiler.
Yeah.
Well, thank you everybody for joining this webinar. My name is Nahuel Losano. I'm a PhD student in geology at Universidad Nacional del Comahue, supported by a CONICET scholarship. I'm also part of the environmental research group, where I'm working on my PhD project under the supervision of Dr. Gustavo Villarrosa and Dr. Deborah Bate. My research focuses on the occurrence of hydrogeomorphic events in fluvio-lacustrine systems of northwestern Patagonian Andes affected by recent volcanic eruptions. Following this line of inquiry, I'm going to present today a basin-wide sedimentological and stratigraphic analysis of tephra remobilisation throughout northwestern Patagonian fluvio-lacustrine systems. Well, northern Patagonia is frequently affected by the explosive activity from the southern volcanic zone, which is characterized by large volume eruptions. These episodes of intense volcanism may lead to different volcano hydrologic events triggered by the remobilisation of tephra deposits, not only in volcanic proximal areas, but also in a broad region of the northern Patagonian Andes. These events constitute a hazardous processes, as they can damage infrastructure and interrupt road traffic. So understanding these events is important, is relevant for developing efficient mitigation strategies and protecting vulnerable populations. Since the recurrence period of these major eruptive events is often longer than the time covered by the historical data, an integration of the sedimentary record is essential, is fundamental for reconstructing the occurrence of these phenomena over an extended time frame. So in this work, we attempted to trace airfall tephra and remobilized tephra deposits through two fluvio-lacustrine systems, Totoral and Las Piedritas watersheds, through extensive riverside sedimentological surveys and through sedimentological limnogeological studies that included taking a sediment core from a wet meadow located in the delta plane of Las Piedritas watershed using a Livingston piston core, and taking another one from the Pro-Delta environment using a Nuvitec core. Extremely poorly sorted and metric-supported beds composed of both epiclastic and pyroclastic material occur as two distinct deposits as Las Piedritas outcrops in a low-gradient confined channel setting. They are composed of lapilli, coastal lapilli, and epiclastic blocks dispersed within a syneritic epiclastic matrix. And shower-bedded tephra layers were found draping each of the two chaotic intervals, showing an exclusive pyroclastic composition and no sedimentary structures or fragment roundness. A large part of the study area remains covered by the 2011 Puyehue-Cordon-Cauche tephra, constituting a significant feature of the current landscape. As observed in the Totori watershed, thick packages of this remobilized pumiceous material overlay the horizontal surfaces of the alluvial plain and lower terraces. These units can reach 1.3 meters thick and are almost entirely composed of tephra, and an equivalent deposit is found along Las Piedritas floodplain, and its remarkable thickness was corroborated by taking the sediment core at the wet meadow in Las Piedritas delta plain. Naturally, an analogous expression of those thick remobilized pumice deposits was expected to be found in the subaqueous portion of Las Piedritas delta, but in the 46-centimeter long core retrieved in April 22, we distinguished the presence of pyroclastic material interrupting the fine organic matter-rich background sedimentation, including 7 millimeter to centimeter thick discrete event layers with no remobilization evidence, analogous to the continuous bit-rich units embedded in the outcrops of Las Piedritas watershed. These tephra units correlate positively with the magnetic susceptibility fluctuations and negatively with the water and organic matter content. So they can be traced by peaks on the magnetic susceptibility profile and by troughs on the other parameters. The continuous and widespread occurrences of the vitric-rich units embedded in Las Piedritas riverside outcrops and the lack of reworking features that is also described for all the tephra deposits within the lake core indicate an airfall origin. While the pyroclastic composition of the two conspicuous intervals within Las Piedritas outcrops suggests that they resulted from discovering and reworking of previous tephra bed, and the appreciable mixing with epiclastic components indicates entrainment of upper basin regolith derived debris as well. The disorganized pattern and extremely poor sorting observed in these deposits are consistent with the laminar nature of gravity-driven high concentration flows, and they originated from large runoff processes and due to erosion and sediment incorporation evolved as lahars capable of suppressing turbulence, preventing better organization and internal segregation of the deposits. The fibric and compositional difference noticed between the prominent pumice lapilli deposits caping the floodplains and the laharic deposits documented upstream reveal a hydrologic tephra remobilization process that is rheologically different from a secondary lahar. Such thick and laterally discontinuous tephra-dominated beds result from the overflow of streams carrying a floating pumice load. Here you can see, as it was clearly observed during the 2011 Puyehue-Cordon-Cauche eruption, in the proximal to mid-volcaniclastic environments that we study here, the occurrence of this phenomenon that occurs during eruptive events when large amounts of this high porosity and lightweight material reach the active fluvial channels. Due to its positive buoyancy, the pumice flow does not mix with the stream flow below and is transported as a slowly moving overlying mantle. So to conclude some final remarks, different volcaniclastic phenomena might result from the tephra fold accumulation in proximal to mid-volcanic settings, runoff processes originating upstream from heavy rains or snow melting may involve erosion and entrainment of pyroclastic materials and consequently lead to lahar formation. The occurrence of past analogous events in Las Piedritas watersheds is documented in a low gradient confined channel setting, and remobilized pumice flow deposits resulting from the syn-eruptive overflow of streams carrying a floating tephra load fill the flatter low-lying environments. Although large amounts of remobilized tephra were found in the subaerial portion of both watersheds, no reworked tephra unit is recognized in the sediment core obtained from Las Piedritas Pro Delta. Maybe large amounts of the flotation remobilized tephra were retained in the delta plane, while another considerable load would have been carried away from the creek mouth under the influence of dominant regional winds. This we would count both for the lack of secondary tephra deposits and the low primary thick of the 2011 Puget Cordon Cauche products. And that's all.
Thank you very much, Nahuel. Another very interesting presentation that we've seen. So the chat is open once again. If you have any questions, please write them down, and I will read them to Nahuel. But while we wait, I have a few questions for you, if it's okay. I am not a specialist on that at all, so I'm quite curious to know, because you present fluvial and lacustrine environment, but can you find similar pyroclastic evidence in marine settings? And for example, can you find that into I would think more into shallow marine or maybe lagunal system, or it's too far from the source?
In this setting is too far due to the regional distribution of the winds. Most of the pyroclastic clouds are carried to the continental side. Okay. But maybe in other settings can be possible to trace this phenomenon also.
Yeah, so it was more a general question, not particularly like, can you find this sort of evidence in marine environment? But is it I guess they won't form like thick deposit like this amazing picture that you show, that there will just be maybe some particles, some sedimentary particles that will be found in lagoons, for example?
Yes, I can imagine that. I haven't read a work like reporting this kind of phenomena in that environments, but I can imagine it could be possible.
Yeah. And then yeah, that's also a general question. It's not particularly, but how far can you find tephras or pyroclastic evidence from the source?
Here we are almost 46 kilometers away from the volcanic source, but you can find it 60 kilometers away also.
Okay. And yeah, at the end you show that there is some that I'm really not familiar with the nomenclature. I'm sorry, but yeah, thank you. If you go back to your conclusion slide, please.
Okay. Yes.
Yeah, the flotation remobilized tephras, that they can float, like if we consider like indefinitely, or at some point they will be too wet and they will sink.
At some point they sink.
Yeah. And that, for example, how far can they float and then sink from the source, where they were remobilized?
They can be transported very far downstream under the influence of the regional winds. because
Okay,
they are carried out. In this case, for example, the tephra, the floating tephra, is carried away from the mouth creek under the influence of the regional winds, and they constitute like pumice raft.
Okay. So we have a question that came from Ross Campbell from Ontario in Canada. Thank you for an interesting presentation, Nahuel. How fast does the volcanic material weather to become soil in this environment?
Sorry, I didn't understand the question. I will read it.
How fast, if you want to read it, how fast does the volcanic material weather? So how fast does it take, how long does it take for to be remobilized, to be eroded and then transported, and to be redeposited as a soil?
It can be really fast. For example, the deposits of the 1960 eruption of the Puget-Cordon-Cauche eruptive center is already part of the soil environment.
Okay. So we are arriving, yeah. Ross is thanking you for your answer. So we are arriving at the 5 minutes of the question. So thank you very much, Nahuel. If you have any more questions for Nahuel, please write them in the chat, and we can read them at the end of the presentation of the.
Yes, you can also check the last publication by our group, which is open access in the positional record.
Yeah, and there is the DOI link on the chat.
Thank you.
So thank you very much. So if you can stop sharing, yeah, and then Nemi, if you're here. So the next presenter will be Nemi Walding. If you can start to share your screen. Yeah, perfect.
Yep.
Yeah, so it's up to you.
Thank you. So yeah, thanks to everyone for coming. So my name's Nemi Walding, and I'm a third-year PhD student at the University of Hull. And I'm looking at how the influence of moisture on pyroclastic density current deposits has implications for understanding volcanic stratigraphy. So what is a pyroclastic density current, or a PDC? So a PDC is a volcanic hazard. They're a multi-phase flow, so this means they've got a gas, liquid and solid component. And they can travel really fast, and there can be a range of temperatures, but famously up to quite high temperatures. And they have the ability to travel over large distances overseas and can summit topographic barriers. And because they're quite hazardous, so we need to understand them because there's people still living at risk and living in hazardous areas surrounding these volcanoes. And with better understanding of PDC behaviour, we can feed this into better volcanic hazard assessment. When we think about understanding PDCs, we can think from process to product. So process is the observable eruptions, so the formation of a PDC. But I don't want to be close to a PDC. They're quite hazardous, so it's quite difficult to see them, and they're quite unpredictable. And then we have the product, is what we observe in the volcanic record. So as volcanologists, we go out and we look at quite detailed stratigraphy and begin to unpick the behaviours, unpick the deposit and try and relate them back to behaviours that are happening in the transport and depositional processes. And a key part of understanding the depositional record of a pyroclastic material is called a flow unit. So this is our flank of our volcano. And we have a PDC coming down, and then we have our ash layer, so that's one flow unit. Then we have a changing composition, and that's 2 flow units. And then we have a big scouring PDC that comes, and that's 3 flow units. So one individual flow unit equals 1 PDC moving in that area at that point in time. And they're delineated by hiatus in activity. And they're useful because they can tell us the activity of PDCs in a volcano. So a PDC, a volcanic volcano might be more active in PDCs if it has 10 flow units in comparison to 2 flow units, for example. But we don't always see this. So PDCs especially unsteady, like long sustained PDCs show waxing and waning. So this is an increase and decreases in certain parameters. So it may look like something like this. Here again, we have our flank volcano and our PDC, and it increases in activity and then decreases. And we're left with a different and more confusing layout of these flow units throughout the deposit. And we see there's a different number of flow units at different locations. And this can be contradictory depending on where we are in this deposit. So if we're standing up here, they might only see 5 flow units compared to 2 in more distal areas. And what I want to investigate is how the addition of water affects this deposit architecture. So the introduction of moisture into a PDC system can be through pre-eruptive ground conditions or through influences from the atmosphere. And we see evidence of this in pyroclastic deposits through what we call accretionary lapilli. So these aggregates are ash aggregates, and they form in the presence of moisture, or they can form in the presence of moisture. And so the first bit of work I did, I looked at a suite of volcanic material. So we've got changes in size down the bottom and the addition of moisture on the top. And I did some simple geomechanical experiments to begin to understand how pyroclastic material changes in the presence of moisture. And basically what we found was that small percentages of moisture leads to fundamental changes in physical properties, and the cohesivity of this material changes drastically. And this can lead for the material to be free-flowing to non-flowing as well. And you can read more about that here as well. And what we've recently found when looking at a broader range of pyroclastic material is that fines content controls and has quite a significant impact on this behaviour, and that's in dynamic, so dynamic angle of repose, and static angle of repose environments. And so as we can see here, with the high fines content, we start to see this divergence and quite unusual behaviour happening. And these results begin to indirectly influence the geomechanical properties, and we can begin to think of things such as internal angle of frictions and their behaviour on cohesive related strength. And so here again, we've added moisture to the equation, and what we can see, we're still getting this kind of decrease in angle of repose, and therefore maybe a decrease in internal angle of friction, which is quite important in understanding shear strength of a material. So naturally, we then moved on to looking at variations in shear strength, and what we found in some of this material was with the addition of moisture, our shear stress is significantly less than that of dry material. So this is our shear test, and it's a ring shear, so we can infinitely shear a material. This work is ongoing, so I'm still looking at these results. And some exciting part of my research has been using this fluidized flume. So we're able to fluidize the material and replicate behaviors of PDCs, and we run our fluidized current over a deposit, and we're able to set this deposit in gelatin, and we can slice up the deposit, allowing a 3D view of what's happening between the substrate and the flow. And we also added moisture to the substrate and completed these, and this is a graph just showing how runout reduces with increasing moisture content in the substrate. And this is what this looks like. So this is one of my sections of my flume. So this is our deposit. And what we can begin to see is these really detailed interactions between our substrate and our flow. And we can start to look at feature angles and aspect ratios. And we can begin to unpick how water affects variations and contacts at this boundary, how these have significant implications for understanding deposit architecture. So whether this substrate material is more or less likely to be eroded or preserved. And if we link that back to what I showed you earlier then, so we have our current and we introduce moisture, how likely then is this, or what I've shown you from my previous work, is this moisture influence layer less or more likely to be eroded or preserved? And we think it has quite an enormous potential in affecting deposit architecture of PDCs, PDC flow unit behavior. So yeah, thank you very much for listening. I think I went a bit quick there. But yeah, thank you to everyone involved. Thank you for coming. And also, if you're interested, we have the IAVC Commission on Volcanogenic Sediments, and we're a global community who share common interests on all research on sediment aspects of volcanic phenomena. So if you want to get involved and see more research about that, if you guys are here, you might be interested in that as well. So it'd be great to hear from you. Thank you.
Thank you very much again for a very good presentation. So again, the chat is open. If anyone has a question, please write them down and I will read them to Nemi. While we wait for the questions, I can ask you some maybe some basic questions, I think, for you. But you show that there will be a change in geomechanical properties in the PDCs if they are moisturized or if they are not. But is there also a change in the distance they can reach from the end? How impactful or how important is that for I don't know, environment or communities?
Yeah. So yeah, interestingly, I showed you that kind of our run out distance with moisture in the substrate, and how if we have kind of a wet substrate that can reduce run out distance. And yeah, and that does have an implication for communities, for sure. One thing we are lacking in my experiments is the impact of like the input of temperature. So we are then kind of removing all inputs of pore pressure formation, which might actually enhance run out distances. So yeah, my work's very much a first view of looking at this run out with moisture, but I don't cover all the variables that could be used.
And I guess the answer is no, but is there any way to measure one of these one of these flows in nature?
I think some people in New Zealand have just started doing it.
And do you know how that works? Because that sounds quite dangerous to me.
Yeah, I think it's as a byproduct of something else. So it's from maybe seismic reading that happened to be in the area, not directly related to the pyroclastic current. I know some researchers who want to be able to explore them using methods in it, but I think it's quite difficult. So.
Okay, so there are some questions that came on the chat. So from Stephen from Derby, thank you for presenting some very interesting research. Sorry if I missed this. Does a biological component, for example, forest, have an effect on the flow biolubricant?
Yeah, so in that image I had of the PDC running down and all the influences of where moisture may come from, I do have trees in there. And that's simply because we know that like pyrolysis happens at quite high temperatures. So I'm assuming that maybe some moisture content may come from that, if that's what you're asking. Probably not a lot, but in terms of maybe once the PDCs cool down and pyrolysis is happening and water's being evaporated, we might see some localized influence from like trees and forests and stuff.
Good, thank you. Then there's another question from Nils that presented earlier. Great talk. Did you find whether changes in chemical composition of PDCs have any influence on depositional architecture?
Yeah, so chemical composition is something I'm looking at now, and I've explored, after my first paper, I've now explored a wider range with a wider range of chemical compositions. And we are starting to unpick those slight changes in chemical behaviors, but I'm not a chemical chemist or geochemist, so I haven't gone into details. I think maybe that in some cases we see more scavenging minerals, so in like hydrothermally altered deposits, we might get these scavenging minerals that might kind of scavenge water, but that will be beyond my research, I think. But it's an interesting point.
Okay, thank you. There is another question from Isaac from the US. Great talk. could specific types of volcanic conditions influence moisture content?
Yeah, so we get volcanic eruptions called phreatic and phreatomagmatic eruptions, and they form when the magma kind of is in contact with groundwater, and they're often really explosive, and they're known as wet eruptions, and they often have a lot high fines content as well. So especially with what I was saying earlier, when fines really seem to be quite important where moisture is concerned. It'll be interesting to explore that a bit more, and I've got future ideas exploring that. But yeah, so volcanic conditions, yeah, do influence moisture contents.
Okay, thank you. And then there is a follow-up question. The follow-up question. And does this influence the grain size distribution and sorting?
Yeah, so in these phreatic eruptions, we get finer, more ash material, and that's more likely to have a smaller grain size distribution and higher sorting, I guess.
Okay, maybe I think it will be the last question, like from Ross from Ontario. Thank you, Nemi. Are there implications of climate for the severity behavior of these flows? My understanding is that is there any difference in the behavior of how the PDCs will behave if it's a tropical climate or if it's desertic climate?
Yeah, okay. So I've looked a lot at looked kind of the influence from a more humid environment. So I mentioned briefly those ACLAP, so accretion lipili, those little circles of ash that accumulate together. They form in more humid environments and to do with rain. So therefore, that if we're thinking in terms of that, then we're more likely to get moisture involved in a current that way. Yeah, sorry, I probably didn't answer your question that much. I'll be happy to talk to you about it in more detail if you want to.
Okay, thank you very much. So I think we can conclude the webinar today. So thanks a lot for all the presenters.